When is transient heat transfer analysis necessary? Have you ever wondered when you need to take a closer look at how heat moves through materials? Transient heat transfer analysis is key when temperatures within a system change over time. This means that the thermal conditions are not constant but evolve. Unlike steady state heat transfer where temperatures remains unchanged once equilibrium is reached. There are several situations where this type of analysis is essential. First, consider when the initial temperature distribution impacts the outcome. For instance, heating a pot of cold water versus hot water on a stove for the same amount of time will yield different temperature profiles. Transient analysis captures these time-dependent changes accurately. Next, think about thermal loads or boundary conditions that vary over time. If the heat input or environmental conditions change dynamically, transient analysis helps model how the temperature responds as time progresses. Another important factor is the heat capacity of materials. Transient heat transfer takes into account how materials store heat, which affects how quickly temperature changes occur. This is particularly relevant in systems where thermal transients impact performance or safety. For example, electronic devices generate heat during operation, and understanding this heat transfer is vital for maintaining performance and safety. When designing or analyzing systems, knowing the time-dependent distribution of temperature is critical. This includes predicting hot spots, cooling rates, or thermal stresses that develop over time. From a mechanical engineering perspective, transient heat transfer analysis involves solving time-dependent differential equations that consider conduction, convection, and sometimes radiation. The process begins with defining the problem and geometry, including materials and heat sources. Next, a mathematical model is formulated based on the conservation of energy and heat transfer laws. Initial temperature conditions and time-dependent boundary conditions are then applied. The model is solved using analytical or numerical methods to obtain the temperature distribution as a function of time. Finally, results are interpreted to assess thermal behavior and design effectiveness. In practical terms, transient analysis is crucial when the timescale of heating or cooling is similar to the thermal response time of the system. For example, in electronics cooling, this analysis predicts how quickly a device heats up during operation and cools down after shutdown. This influences design choices for heat sinks and fans. In manufacturing processes like welding or casting, transient thermal analysis predicts temperature gradients and cooling rates that affect material properties and residual stresses. In summary, transient heat transfer analysis is necessary whenever temperature changes over time influence system behavior, performance, or safety. It provides a more complete understanding of thermal phenomena compared to steady-state analysis, which assumes constant temperatures.